Hi, today we will find order pairs AB that will make 4a minus 1 over b and 4b minus 1 over a are both integers. So first, we set 4a minus 1 over b equals k and 4b minus 1 over a equals L, where a and b are positive integer. If a and b are positive integer, then KL must be greater or equal to 1. We notice 4a minus 1 and 4b minus 1 is always odd. Since the numerator part is always odd, then a and b must be odd to have a solution, which is k and L must be an integer. Therefore, AB and KL must also be odd, because 4a minus 1 over b is always odd, and 4b minus 1 over a is always odd. We rearrange the first equation into b equals 4a minus 1 over k, and we substitute b into the second equation, become 4 times 4a minus 1 over k minus 1 all over a equals L. And negative 1 is same as k over k, become 4 times 4a minus 1 over k minus k over k all over a equals L. We bring the k into the denominator. The equation become 4 times 4a minus 1 minus k over ak equals L. Distribute 4 become 16a minus 4 minus k over ak equals L. We transfer k into the right hand side and we divide each term by a, become 16 minus k plus 4 over a equals KL. From the first part of our solution, k and L is always greater or equal to 1. So we can say that the product of KL is also greater or equal to 1, and k and L is always odd. Therefore, the product of odd is always odd. Since 16 minus k plus 4 over a must never be negative integer, we can say that KL is in the range of 1 to 15. Since KL is in between 1 to 15, we can say that k is in between 1 to 15. And the term k plus 4 over a must also in between 1 to 15, such that we will not make KL a negative integer. Since k is an odd integer, it must be in the form of 2n minus 1, where n is in the element of 1 to 8, still satisfying k must be in between 1 to 15. Substitute 2n minus 1 into k plus 4 over a, become 2n plus 3 over a, which is still between 1 to 15. Since b equals 4a minus 1 over k, then we can substitute k, become 4a minus 1 over 2n minus 1. So far, we need 2n plus 3 over a and 4a minus 1 over 2n minus 1 are both integers. Now, we must have 2n plus 3 over a must be an integer, and 4a minus 1 over 2n minus 1 must be an integer. N is inside 1 to 8. Now, we will find the order pairs AB by substituting n into our given conditions. When n equals 1, 2n plus 3 over a become 5 over a, and 4a minus 1 over 2n minus 1 become 4a minus 1 over 1. The only integer that will make 5 over a an integer is when a equals 1 and a equals 5. we must also satisfy the second condition. 4a minus 1 over 2n minus 1 must be an integer. Under n equals 1, we have order pair 1, 3 and 5, 19. Since 4 times 1 minus 1 is 3 over 1, still 3. And substituting 5, 4 times 5 is 20, minus 1 is 19. When n equals 2, we have 7 over a and 4a minus 1 over 3. The only integer that will divide 7 is 1 and 7. So we have order pair 1, 1 and 7, 9. When a equals 1, we have 4 minus 1 is 3, divide 3 is 1. When we have 7, 4 times 7 is 28, minus 1, 27, divide 3, give 9. When n equals 3, we have 9 over a and 4a minus 1 over 5, which give order pair 9, 7. In the first condition, 9 over a, we have integer when a equals 1 and a equals 3. But a equals 1 and a equals 3 does not satisfy the second condition, which give a fraction. That is, 4 times 3 is 12, minus 1 is 11, 11 over 5 is non-integer, same as 4 times 1 minus 1 is 3 over 5. Under first condition, we must have a equals 1 and a equals 11. 4 times 1 minus 1 is 3 over 7, a non-integer. When a equals 11, 4 times 11 minus 1 is 43, which not a factor of 7. So under n equals 4, we have no solution. And we will repeat the process until n equals 8. You can try checking one by one, but I will give it to you given. So finally, order pair AB is 1, 1, 1, 3, 3, 1, 5, 19, 7, 9, 9, 7, and 19, 5, total of 7 pairs. These order pairs will satisfy 4a minus 1 over b, an integer, and 4b minus 1 over a equals L. We can check. We can choose 3, 1. 4 times 3 is 12, minus 1, 11 over 1 is 11, an integer. 4 times 1 is 3, over 3 is 1, an integer. This total 7 pairs will satisfy our problem. Finally, we find them all. Thanks for watching.